let's get going. A little light today, but I will. Yep, we are going to talk about when assumptions are violated. Alright, so when assumptions are violated. Quick review on Anova. Hopefully we don't need it, but Anova is used when we have this question of are the means equal, or does some variable have an effect on the dependent variable? And our variables are categorical, so that's our grouping level, and then we have some sort of measurement variable. All right, so null hypothesis of an Anova is that all means are equal. The alternate is that at least one mean differs from the rest. Before we proceed, we check our assumptions. 3 assumptions are that data are random and independent, which we're not going to worry about this semester. Data are normally distributed within each group. We use quantile plots to look at those. And data are homoscedastic, or they have equal variances. We have our options are Brown-Forsyth test or Fligner-Killeen. The decision comes down to our previous interpretation of the normality assumption. All right, when we run the test, we have an F statistic. We've got 2 degrees of freedom. We're going to have our p-value, and we report basically all 5 aspects. And in order to run it, we do our 2-step process. We first make a linear model, and then we generate our Anova table. So the question you could be asking is why do we worry about the assumptions? Why are they so important? And why do we always check them before we start running the tests? All right, so it comes down to the test statistic. That's what's important. So if all of our assumptions are met, then that F statistic that we get, that ratio of the mean squared treatments to the mean squared error, is going to follow an F distribution. All right, so here's an example. I just generated random F statistics from a data set. So basically took a data set, randomized it, and just generated about 10,000 F statistics. And this is what the distribution of our F statistic looks like. I overlaid the F line, the F distribution line. I did the same thing as what we did when we overlaid the normal curve. So we used hist, and then we did curve and add equals t. Same thing. Well, I also looked at the QQ plot, because QQ plot allows us to assess our assumptions, or assess normality, assess how our data fits to a theoretical. So if we follow this distribution, all of our points should be on that line and within our confidence envelope. So you can see it. If all of our assumptions are met, then our F statistic from random samples will approximate this actual F distribution. Our p-values will be correct. But if we're not, then our F observed won't follow this F distribution anymore. And we've got this. So now I've generated a data that no longer meets our assumptions. And while the histogram looks like it might do fairly well with the F distribution, the QQ plot reveals that we're no longer following this distribution. Whoops. And that's right here. All of those points fell outside of our confidence envelope. If this happens, and if we no longer follow that F distribution, then our p-value is going to be incorrect. So where did our p-values come from? Well, we basically have an observed test statistic. We'll put it right here. Mouse pointer is a pen. Let's say that's our observed is right there. Our p-value is this area under the curve to the right of that line. No big deal if we utilize the F distribution to approximate our p-value. That works. But if we violate our assumptions and we get an F value like that, well, our histogram, our random F values, don't follow that F distribution. So our p-value could be wrong. And thus, if our p-value is wrong, our conclusions can be wrong. All right? So what are our options? As we check these assumptions, all right, and we violate normality or we violate homoscedasticity, what are our options? And just quickly, I have this in our handouts, but first assumption, random and independent, we won't address that. There's other things that we can do to fix that. But what if we violate homoscedasticity? Well, if we only violate this assumption, then we have a Welch's Anova that we can run. And we have a corresponding Welch's t-test that we can run instead of a regular Anova. If we violate normality and only violate normality, then we have a couple different options. We can proceed with Anova, which is fine, because Anova is robust against this violation of normality. And you could say, well, hold on, well, how bad do we have to be? How non-normal do we have to be in order to avoid using Anova? I'm going to say you have to be pretty bad. Most real-life data probably don't have to worry too much about. Your data was very obvious, and I mean that the underlying data wasn't normally distributed in the first place, so I wouldn't worry about that. But if we're just slight to moderate, one of those where it's like, yeah, I think it's non-normal, and you're pretty confident that it's non-normal, you could probably proceed with Anova. There's also a non-parametric alternative called the Kruskal-Wallis test. It's kind of like a sign test in that it compares the median. But unlike the sign test, it allows us to compare medians between multiple groups. That's fine if we want to compare the medians, but if we're still set on comparing the means, then we're going to have to run a permutational Anova. All right, so this is going to be the start. And what happens if we violate both homoscedasticity and normality? Then basically our only options to run this permutational Anova. And that has a pretty significant effect, because if we're going to violate our assumptions, I left you space to kind of go back and fill in these answers. But if we violate one of our assumptions, then we violate it for all of our post-hoc tests too. So if we're going to adjust what test we run, so instead of running an Anova, if we're going to run a Welch's Anova, then we have to remember that Tukey's won't work for us anymore, because Tukey's assumed equal variance. That was violated. All right, so what do we do? So why worry about our assumptions? We worry about them because our F statistic follows an F distribution with df1, df2 if assumptions are met. If not, then if assumptions are not met, then our F stat does not follow the F distribution. And that again is df1, df2. And thus our p-value can be wrong. Pretty significant. All right, so what are our options if we violate the assumptions? See below. All right, and just remember, I've added a note. Our post-hoc tests also have assumptions that must be met. So if we test our assumptions for Anova and they are met, then we assume that they're met for Tukey's. If we violate the assumptions of Anova, then we also violate the assumptions for Tukey's, and we have to do alternative comparisons. All right, so assumption number one, random and independent. What happens if we violate this? One, we can redesign our experiment. Might not like doing that, but if you can't fix it statistically, you're going to have to fix it methodically. I know it's methodically, but I don't know. It kind of has a different meaning. You're going to have to basically go back to the drawing board and fix it. All right, to try to avoid that random in it, to try to avoid being non-random or non-independent. All right, but statistically, oftentimes we can utilize what are called mixed effect models, which accounts for this non-independence and the non-randomness. And again, we won't address this violation of the assumption. If you're doing a research project and this comes up, then I'll help you with these models. All right. What happens if we violate normality within each group? So again, our assumption is normality within each group. So if we violate normality, we can proceed as normal. as usual, and it's because ANOVA is robust to violations of this assumption. That's why. Second option, if you want to be careful, and sometimes you have a reviewer that says, well, you're not normal, you can't use ANOVA. Second option that you could do is something called transform the data. So what we would do is apply a function to the dependent variable and then recheck the normality assumption. The example of this that we often see is to take the log or ln of the measurement variables. That would be the most likely scenario. You take the log or the natural log because your data are on such a large scale. The log or natural log will help to compress it and try to get us closer to normality. So sometimes it's not going to fix it, but sometimes it gets us much closer to where we can then run ANOVA as usual. This is usually one of my first things that I try to do because it's somewhat easy. It's easy to apply one of these functions in the code. We're not going to really mess around with it in this class because our third option is also just as easy, which is to run a permutational ANOVA. And this permutational ANOVA is basically generating our own null distribution using our own data. Now it sounds daunting, but I'm going to give you a script for this permutational ANOVA where we only have to change like 2 lines. And that change is just specifying what our independent and dependent variables are. And then we run it and we get our p-value. So, this is why if we're close enough, I could run regular ANOVA, but if I want to be extra cautious, we can run a permutational ANOVA. Computing power is good enough to where we can run this very, very efficient. That's if we violate normality within each group. If we violate homoscedasticity, my recommendation is just go ahead and always run Welch's Anova. And Welch's Anova is your standard ANOVA, but it adjusts the degrees of freedom to account for the unequal variances. So some of you may have run t-tests in Excel, using the data analysis tool package. So in that packet, we have t-tests, and then it says 2 sample assuming equal variance, 2 sample assuming unequal variances. Well, the unequal variances is this Welch's t-test. And for us, there's an equivalent Welch's ANOVA that allows us to compare means between 3 or more groups. What happens if we are non-normal and heteroscedastic? So non-normal and unequal variances, permutational ANOVA. Now, permutational ANOVA can also apply for the homoscedasticity. And I'm going to put that in parentheses because I don't actually prefer it. And the reason is that once we go down that permutational route, that randomization route, then we should continue with the randomization route in all of our post-hoc tests. If we just use Welch's ANOVA, there's a comparable Welch's t-test that we can use as post-hoc tests, but we'll have to adjust p-values to get us back to that 0.05 level. So I recommend Welch's ANOVA, but again, permutational ANOVA could also work. If we violate normality and equal variance assumption, permutational ANOVA, that's what we're going to have to do. All right, so our first data set that we're going to work with is oaks.csv. And actually, if you notice at the top, I listed all of the data sets that we'll work with. So that way you can kind of download them and import them into R all at once. So go ahead, import your data set if you haven't done so. I have to do so. Data. Oops. Make sure you have heading and strings as factors to make sure that it works properly. I'm going to make it lowercase oaks. Gonna copy it, paste it into the code. Oops. Get it back up here, paste it into the code. All right. Libraries. We'll need the car package. We'll need the car package for this. Functions, don't really need them just yet. As I look at it, normality, we left off a Welchs test. When we violate normality, so we'll change our numbers as I thought about it. Put that number 3. Welchs test, that's our non-parametric equivalent. Less power, less powerful, and compares medians. And we'll introduce all of these. Remember that. So yeah, I don't think we need any of the scripts. I don't think we need standard error or anything else. So we're going to start with violating homoscedasticity. So in our oaks data set, we measured oak trees at 4 locations on campus. We want to know if the diameter of oak trees differ between the locations. That was our goal. So what kind of question can we ask of this data set? And I bring this up because this is kind of like our biological question that we will then answer in our write-up. What's that?
What are the variables you have most mind?
Site and diameter.
We're measuring the sides at the same time.
Yep. So if we say, is tree diameter equal at each of the sites? That can work, right? Or we could say the site affect our tree diameter. Right now, we don't necessarily have cause effect, but it gets across the same idea. Does this independent variable have an effect on our dependent variable? So we look at our data, we see that we have 2 variables, site and diameter. One of them's a categorical variable, a nominal variable. One of them's a measurement variable, that's diameter. So we know we want to run ANOVA. All right. So our general workflow is this. We're going to first inspect the data. Once we inspect the data, we check for normality. Then we check for homoscedasticity. We run our tests. If everything checks out, and then if our p-value is less than 0.05, we continue with a post-hoc test. All right. So we're going to start with inspecting the data. How do we inspect our data?
Plot it.
What's that?
Plot it.
Okay, plot it. How do we plot it? Plot what? Diameter as a function of site, where we specify that our data can be found in oaks. And this is what we get. All right, so first question, why do we inspect the data? What are we looking for?
Kind of visible differences.
Okay, visible differences. So this leads to preliminary predictions for our test. So we want to kind of look at it, kind of have an idea of what kind of p-value should we get. If I look at this and I get a p-value of 1, I'm going to be suspicious that I did something wrong. Because I can clearly see that my medians don't line up, and if the medians don't line up, there's a good chance that my means don't line up. So a p-value of 1 means that the means are exactly equal. Yeah, if I get a p-value of 1, something's screwed up. Likewise, if I get a p-value of 0, warning bells should be going off. Right? What if I get a p-value of 0.5? What would I think? Let's change it to 0.4. What's that?
Reasonable.
Yeah, 0.4. Anything above 0.5, I think I start to question, because I'm looking at these medians, I'm looking at the boxes. And this box doesn't look like it doesn't look like these two boxes overlap at all. These, it doesn't look like this box or this box overlaps at all. And when they don't overlap, we're going to probably get a significant p-value. We could go that if our boxes overlap the median of another group, then there's probably no difference. So I don't expect really a difference between these. Questionable between this one and this one, but I think this one's going to fall out. It's not going to be different. So yeah, we get preliminary predictions for our test. Why else do we inspect our data?
Check the assumptions of your test.
All right, we can check assumptions. So with our box plots, we're looking at having the median inside of those IQR boxes. We're looking for equal sizes of our IQR boxes and equal sizes of our whiskers, right? Does that look like that? I'm not going to be surprised if I'm going to get, what, non-normality or unequal variances? Unequal variances. I mean, we're in the section on unequal variances, right? So you can see there's a big difference. There's one other thing why we inspect our data, and what is that? And we've said it a couple times before. Outliers. I'm going to put outliers and data entry problems, because if there was a data entry problem, it's going to probably show up as an outlier, and we're talking about missing a decimal point, or in this case, where our averages were around like between 20 and 30, and we're looking for an accidental decimal point or an accidental extra digit. All right, we're going to see that as like that 1 point way up high in the hundreds, whereas everything else is down in the middle. We're looking for some outliers, but I don't really worry too much if we have a point. Like here, if we had a point up at 35 for this group, I'm not too worried about it. That's just a real data point. We collected it. Maybe I go back and look at the data entry to confirm that I typed it in correctly, but I'm usually not too worried about it. All right, so preliminary expectations based on this based on these data, this plot. I'm gonna probably detect unequal variances and possibly have p less than 0.05 for our ANOVA. All right, so we might not run an ANOVA, but we're kind of getting across that we might have unequal variances. And when we do the appropriate test for our assessment of the means, we might find a difference. All right, so we looked at our data. That was step one, inspect the data. Now go ahead and check normality and check homoscedasticity. You should be able to do that. I left your boxes to kind of go through and do that. I didn't run my car library. All right, did you get it? Right, QQ plots. Oh, come on, move it over here. All right, QQ plot diameter is a function of site, data oaks. They all look like they fall inside of those confidence intervals. I can enlarge it if I wanted to, but I don't think I need to. If we wanted to do this, so this is our conclusion. Data appear to be normally distributed within each group. Wanted to view a larger image of each, or a larger plot of each. I would do something like this. Diameter as a function of site, data is oaks, and then subset equals, I'm going to use parentheses here, site equals A. Not going to work. Yes, QQ plot doesn't. Subset works. Oh, you know what? I know what it is. We'll do that. We'll do this later. We're going to use the subset function. So what we will do is have to be TBD because we're going to talk about the subset function. All right. So, and I'm going to show you how to do that because we're going to need to do that when we do our pairwise tests. So I know this is coming up. Just, we'll come back to this. But I think for this, we're good. We're good. Brown-Forsythe, Levine test, center equals median. What's our conclusion? Yeah. Data are heteroscedastic. All right. So we reported Brown-Forsythe. We've got our F value. We've got 3 and 234. All right, that's our degrees of freedom. 19.99, and P is less than 0.0001. So pretty small. All right. Anova is sensitive to the assumption of equal variance. If we violate that, Anova is going to really get screwed up because it utilizes variances to determine if our means are different. And it kind of makes the assumption that you have the same amount of variation around each of the group means to generate these sums of squares and the mean squares and so forth. We can still generate those if our variances differ, but we're not going to follow that F distribution anymore. The ratio is not going to follow it. So if we only violate this equal variance assumption, our preferred option will be to run in Welch's Anova. Welch's Anova is going to answer the question, are the means equal, or does the independent variable affect our dependent variable? It's the exact same thing as Anova. It has the exact same variable, so one categorical variable, one measurement variable. It's going to work if we have 3 or more groups. It'll work if we have 2 groups. All right? It has the same null and alternate hypothesis. So our null is that all means are equal. Our alternate is that at least one mean differs. Our assumptions of this test is that data are random and independent and that data are normally distributed within each group. And we use quantile plots. So really, the only assumption that doesn't apply is that we have equal variances because Welch's Anova will fix that. Now, I do put a note that Welch's Anova adjusts for this unequal variance, and that even though we're making this adjustment, the power of the test is going to be very similar to the power of a regular Anova. And this is why some people actually prefer and recommend running Welch's Anova all the time. They just say, well, if you're going to run Anova, go ahead and run Welch's Anova just to guard against those slight deviations. So if you don't have exactly the same variances, we know they're going to be slightly different. Run Welch's. All right. So some people would say, go ahead and run Welch's Anova because we guard against making an incorrect conclusion. But kind of the consequence of this is that we're going to be a little bit more conservative, meaning it's going to be harder for us to reject the null hypothesis. And some people are okay with that because the likelihood that we get a p-value right around 0.05 is usually pretty small. And it can happen, but I haven't really seen a huge number of tests that generate a p-value like that, unless it's on an exam. Then you have to make a decision. So we've got the same type of assumptions. Test statistics are going to be the same. We're going to have an F statistic. We're going to have a degree of freedom 1 and a degrees of freedom 2, referring to our numerator and denominator. But note that degrees of freedom 2 is going to be a decimal number. So degrees of freedom are usually all whole numbers because they're tied to our sample sizes. Welch's Anova is going to change that to a decimal. So when you see a decimal as a degree of freedom, you should think that we're probably doing a Welch's test. And then reporting, we report the same thing as we do for our Anova. So conclusion, interpretation, the test statistic, both of our degrees of freedom, including the decimal, and our p-value. Now, how do we run it? It's going to be a little bit different. We can't make a linear model and then view the Anova table. That's not going to work. So in order to run this test, we have to use a function called oneway.test. And we write it as a formula where we're testing the effect of x on y. So y is a function of x, we specify our data, and then we say var.equal equals false. Now we've seen this before, where var.equal equals t, when we ran like a t-test. But var.equal equals false tells R not to assume an equal variance. And I'll tell you that this oneway.test was written to do an Anova. It was written. So you can ask, well, why did we learn how to make a linear model and view the Anova table if it already has this oneway.test in it? That's a valid question because this is a one-way test. If we start adding a second variable to do a two-way Anova or we add a covariate, this no longer works. So if you understand that you can run an Anova using the linear model, then we can start doing even more complex models using that same code. All right. So here's our Oaks. Let's run our Welchs Anova and see what it looks like. So we're going to run one-way.test. It's built in to R, so we didn't have to load anything. We're testing the diameter of our trees as a function of site. We find it in the Oaks data set, and then var equal equals false. And that's our default. So I run it, and I get this output. So a little bit. Rerun it, see if I can get it all on. There we go. So it gives us our test name. We did a one-way analysis of means not assuming equal variances. We should recognize that as Welchs Anova. We tested diameter and site. We have our F statistic. That's our observed F statistic. We've got a numerator degrees of freedom, DF1. We've got a denominator degrees of freedom, DF2. Note the decimal on there. So we need to report that decimal. And then it gives us a p-value. It's 3.596 e to the negative 15. So this is 3.596 times 10 to the negative 15, which is pretty darn small. So what could be our write-up for this? Okay. Site does have an effect on tree diameter. And it could be for any number of reasons. But we will say Welchs Anova, that's the name of our test. We have our F statistic, and what we have to do is report our degrees of freedom.
Is there a rounding rule for degrees of freedom? Or just should we report the whole number it gives you?
Don't report the whole number. Not when we do the Welchs, because we want to emphasize that we have a decimal, that we actually used Welchs. So I don't ever recall ever saying numerator degrees of freedom being a non-whole number. The only one was always our denominator degrees of freedom. So normally what I would do is report to the hundredths. R reports to the hundredth. I think SPSS also reported to the hundredths. So just go ahead and report to the hundredths, and it'll work. So we have that. And I do put a note here just to remind us about the degrees of freedom. Denominator degrees of freedom, which would be the equivalent of DF2, has decimals, and we had a good question. Report to 0.01. I think that would be a good thing to include. All right, so we have a difference. We're not done, because our process said if we have a p-value less than 0.05, we have to continue to do a post-hoc test. All right, so post-hoc tests. If our p is greater than 0.05 for Welchs Anova, we stop. No difference in means. Stop there. But if we have less than 0.05, then we have to run a post-hoc test to figure out which means are different. So what options exist? We've got two options. All right, we can't run Tukey's because Tukey's assumes equal variance. We violated that assumption. So our two options will either be pairwise Welch's t-test with a p-value adjustment, or we can run pairwise permutational t-test with p-value adjustment. So we got two. My recommendation, I'm going to put an asterisk at this point, is to run pairwise Welch's t-test or Welch's Anova. Or Welch's Anova. And just again, remember that Anova, or a t-test is like a special case of an Anova. We'll get the same p-value. Different test statistic, but we'll get the same p-value. Same thing applies with Welch's t-test and Welch's Anova. So our pairwise Welch's t-test would be preferred because you already ran a Welch's Anova. Easier to explain in the method section. But if you really wanted to do something different, you could always run pairwise permutational t-test, which means we're going to run randomized t-tests. We're going to get a p-value for each comparison, and then we have to adjust it. All right, so both options have us performing multiple tests on the same data set. And we're not talking about using the first two columns in one test and the next two on the second test and the next two on the third test. No, each test is going to be utilizing one column multiple times. One variable in our data set multiple times. Or in this case, we've got sites, like site A, site B, site C. We're going to compare site A to site B, then A to site C, and A to site D. We're reusing that A group, site A, multiple times. When we do this, what error rate is going to be increased? What's that? Okay, what is that? Yeah, our type 1 error rate is going to increase. And we don't want that. This is alpha. Our type 1 error rate will increase because we're making it more and more likely that we falsely reject the null hypothesis. And we don't want that. Now, each test that we run has 5% chance of a type 1 error rate, but collectively, the chance that we have committed a type 1 error is going to start incrementing, going up with every single test that we run. So, after we run all our tests, what we have to do is to adjust our p-values to get us back to a family-wise error rate of 0.05. So this is our overall family-wise type 1 error rate is kept at 0.05. So we're going to run these pairwise tests. We're going to save our p-values, and then we're going to adjust all of our p-values to get back to this family-wise error rate of 0.05. So if you can think about it, what we're doing is lowering our alpha for each individual test just to ensure that the total collection of tests has this error rate of 0.05. So we're going to make it harder for us to reject that hypothesis that the means between two groups are different to ensure that collectively all of our tests, our overall conclusion will have a 0.05 error rate. So how do we approach this? Well, we're going to start with our pairwise tests. In order to run a pairwise test, we're going to make use of the subset function. All right, pairwise. We're going to make use of the subset function. So the subset function, when we give it a data frame, will return a data frame. So if we give it a data frame with 10 variables in it, with 10 columns in it, it will return a data frame with 10 columns in it. But it will only return the data in that data frame that meets the logical statement that we make. All right? So the general code is this. Subset, we give it a data frame, and then we make a logical expression to say, only pick out those data points that satisfy this condition. All right? And I have it being resaved so that dat.ab is going to be our new data frame, and it only has sites A and B in it. So just kind of a good general practice is to make a new data frame and call it something that is more descriptive about what is in there. Yep.
I feel like we've already used the subset. Didn't we use it on the homework that one time to like?
We did. We subsetted to pull out all of the female fish.
Okay.
Yes. That was an easy one because we just pulled out one site. But what we need to do is we need 2 sites because we're getting ready to do a pairwise test. A pairwise Welch's t-test, which only takes 2 groups. All right, so we're going to save our subsetted data as a new data frame. Data is our data frame that we give it, and then the logical, that's a logical expression that only extracts those rows that satisfies the expression. The expression that we're going to write is going to be an OR type of expression. We want to take the row that's where site is equal to 1 value, or site could be equal to some other value. And that means then we're going to have a data frame with these 2 different values. Our logical expression is written in this type of format, where we specify the variable name that we're going to use for our selection. Double equal sign says that it's equal to that value. And then we're going to put the actual value that we're going to pull out in this level. So level 1, level 2, those are the levels within our grouping level factor. All right, our pipe symbol, that's the OR. And that I have that's a key above the enter key. All right. All right. So what we're going to do first is we're going to calculate the mean of the diameter so we can see what we get. So aggregate, we're going to do diameter as a function of site, data is oaks, and function is mean. And this is going to return all 4 sites. All right, and then the next thing we want to do is to pull out sites A and C. Let's pull out sites A and C, and then recheck the aggregate function to see if we succeeded in subsetting our data. Now this is just a check because this is just demonstrating how we're going to do it. So I'm going to call it oaks dot AC, so oaks data frame, sites A and C. We're going to subset our oaks data set. All right, where site is equal to A. Take out those spaces. Site is equal to A, or site is equal to B. Now note that site is a variable in the oaks data set, and we're choosing the functions, the levels that are within site, and we can view that by typing in levels, oaks, site, just to see what we have to use to pull out our sites. These are the same levels that appeared in the plot function as well in the box plots. So, oh, it's not B, it's C. It's A and C. So we're going to do that, and then I'm going to use the aggregate function again. Diameter is a function of site, but this time I'm going to use the oaks.ac, our subsetted data set, just to confirm that when we run it, it only reports A and C. So what this has done is we've taken this data set that has all 4 sites in it, and it's pulled out sites A and C and put them into a new data frame. Now, once we have this, we can utilize the t.test function to run a t-test comparing these 2 means. All right. So what I want you to do is go ahead and create the subsets for each of the other groups, And we're doing pairwise comparisons. So you have your A, B, C, and D. We need AB, AC, AD, BC, BD, and then CD. So we're looking for every combination of our groups, and we should have a total of 6. So what I want you to do is go ahead, write the code to generate these 6 subsets, and then think about what we would do if we wanted to pull out sites B, C, and D all at once. All right, and then what we'll do on Monday is we'll kind of pick up with this, and we'll run our tests on our subsetted data sets, and then we'll talk about adjusting our p-values. All right.